And so today I'm going to talk about the viscous flow in pipes. And to start it, let's talk about what is the flow in pipe. So if we transfer a fluid, which is include liquid or gas, in a classic conduit, um, which is commonly called pipe if the cross section is round, and if it's not round, then we call it duct. So it is very important in our daily operations. So maybe you ask why pipe? So because we use it in our daily life. For example, we use pipeline to carry oils for long distances. Also, for example, in natural system, the pipes that carry blood right throughout our body and also air into and out of our lungs. We use water pipes that coming into our homes, and also the distribution system that delivers water from city well to the house, or in vehicle or machines, in the heating and cooling system in the houses or hospitals or all of the buildings. And this is why it's so important we learn about pipes. So in this chapter, we are applying the basic principles that we just learned in the previous chapters. So let's go through the character to the characteristics of the pipe flow. But just a side note, for all of the flow involved in this chapter, the pipe is assumed to be completely full of water, right? So the pipe is full of water. Okay, now let's see how can we um, classify our flow, right? So the internal flow can be using the Reynolds number. The Reynolds number, it's actually Reynolds was the first to distinguish the difference between these classifications of flow. This is why we call it Reynolds number. So Reynolds, he injected dye into a pipe in which water flowed due to gravity. So if the fluid particle flowing a smooth path like this one, then we we call it a laminar flow. So the laminar flow is just a smooth path in layers, with each layers moving smoothly past the adjacent layers with little or no mixing. So this is why we call it laminar flow. And then if the dye stick if the dye streak fluctuates in time and space, or has chaotic changes in pressure and flow velocity, we call it turbulent. So and then the transitional flow is kind of a mixture of laminar and turbulent flow, but it just it the transitional flow is just when we want to have the turbulent flow, right? It's just the transitional section. So let's see what else we have here. So also we can say that the laminar flow in a pipe, there is only one component of velocity, so we can say that the V is ui. The V is ui, and then for the turbulent flow, it's unsteady, and then it's the I mean it's unsteady and it's random components. So then the velocity is mixture of all the component that we can have. So also we can use the Reynolds number, and Reynolds number rho Vt over viscosity. And then if we use that Reynolds number, we can also characterize the flow, so the fluid flow. So if the Reynolds number is less than 2100, so this is the flow is going to be laminar flow. And if it's between 2100 and 4000, so it is the transitional flow. And then if it's more than 4000, it is a turbulent flow. So this is how we can use this number. And we know that the Reynolds number is a dimensionless number. And okay, let's go to the next section, which is entrance region and fully developed flow. So as we can see in the figure right here at section 1, we can see that the fluid typically enters the pipe with a nearly uniform velocity. So, it's uniform here, it's uniform here, here, and everywhere, right? But then if, for recall, remember I talked about the no slip boundary condition, and we can just see it right here, right? As the fluid moves through the pipe, viscous effects cause it to stick to the pipe, right? So if you can see here and here, the velocity is 0. So it means that it sticks to the boundary, to the pipe wall, right? And then also at the boundary layer, the initial velocity profile changes with distance along the pipe x. So we can see that this is x direction, right? So then it changed from here to here if we look at these two profile. So uh, it changed along the pipe x until when? Until the flow reaches the end of the entrance length, which is LE right here. And then after that, we call it fully developed flow, and then the profile of the velocity is not changing. So in other words, we can say that the shape of the velocity profile in the pipe depends on whether the flow is fully developed or it's at the entrance region. Also, the shape of the velocity profile, it depends to the flow, it's laminar or turbulent. And so it means that it depends the shape of the velocity profile in the pipe depends on if the flow is laminar or turbulent, or it depends on the length of the entrance. No, depends on the length of the entrance. So now these are the important things in this section. And then let's go to the next section. So these are also another way to use the length of the entrance region. So this uh, number here, this is dimensionless, right? Because this is length, the unit, and the dimension is length, and for D is length also, this is dimensionless. And we know that Reynolds is dimensionless also, right? So, and this Reynolds number here, we call it critical Reynolds number because this is when we start to having the turbulent flow. It's just the transitional part, right? So let's go to the next. Okay. So there are three ways that we can provide the important result of the fully developed laminar flow. So these are, we can apply the F equal to MA, Navier-Stokes, and dimensionless analysis. Then we can get the result out of the fully developed laminar flow. So what we have here, we have some variables that I want to, before go to to elaborate this fluid flow, fully developed flow. I want to introduce them. So we have R, which is the radius, the L, which is right here, and this is R. So it's the length of the pipe, and then also it's not a pipe. So if we have a pipe, right, so we choose one small element here like a cylindrical element, and this is how it look like. So let me delete that one, and then the AC, which is the area, is pi r squared, and AS is also okay, one of them is here, right, the area, and the other one is here. So this is going to be 2 pi r L, right? So this is our AC, and this is our AS, right? And then now if we use the conservation of momentum, which we know the formula for the steady state flow is going to be V rho V dot N dA, and we already know that this is the M dot, right? So if I just write down the conservation of momentum and use the force of balance, so here I'm going to get the sigma of Fx, and here I have P1 times AC1 minus P2, because it's, if this is X and Y, our coordinate system, this is going to be negative and this is going to be positive. So this is going to be P2 times AC2, and then also we are going to have shear stress, which is 2 times AS, and then the flow is coming in and going out. So we have, and also the V here, the direction is in this one. So we have um, the minus sign for M dot, right? And then the V1 going to be positive, and then we have, if I write down V2 M dot 2, M dot 2 is coming out of flow, so its outflow should be positive. V2 is going out. This is also positive because the V direction is like this. and so this is why it has a plus sign here. So also it just, if we use the conservation of mass, so one flow is going in and one flow is coming out, right? So it means that m dot 1 is equal to m dot 2. So we can just say that this 2 is going to be 0, and because I mean also v1 and v2 are going to be the same, right, if we use that one. So then v1 and v2 is the same, so this is why it's going to be 0 right here, because the area of AC1 and AC2, they are the same, right? So, and then if we go further here, so we have del P over L, and we have 2 times the shear stress over R. So if we look at the left hand side, del P and L, they are not function of the radial coordinate system, right? They are not function of R. So they are not functions of R, right? So then if the left hand side is not function of R, the right hand side uh, should be independent of R as well, right? So then it means that 2 times the shear stress over R should be dependent of R. So what it means is that tau should be equal to C times R. Then if we put 2C times R, then R going to be cancelled by R, right? And this C is a constant. So if we just use that one, and also if we use the what's the name, the boundary conditions, this is how we get this formula right here. So let's say that at R equal to 0, so we don't have any shear stress at R equal to 0, right? So and also, so it means that 2 is 0, and also uh, at R equal to, this is, sorry, so at R equal to the radius right here, right? Let's say at R equal to D over 2, we're gonna get the 12 wall, right? And it should be maximum there, right? And this is going to be maximum, and we call it wall shear stress. Then if we use these two boundary conditions, we're gonna get C as 2 times 12 wall over D, and then the R, the tau is going to be 2 times 12 wall. We just substitute this one in this equation, in this equation right here. Let me just delete that one, and let me just highlight the equation I need. So then this is also what we get from here, right? So it means that the shear stress distributed throughout the pipe is a linear function of the radial coordinate, right? So it means that shear stress throughout the pipe is a linear function of the radial coordinate. We're going to use this formula after at the end of this section as well. So now, so this is how we can also look at the toe here and the toe wall here, and then also we can see that if it's in viscous flow, so the velocity profile is uniform, right? So that's it from here. If we come here, we're gonna now we are going to talk about the pressure drop and the wall shear stress. How can we relate them? So let's bring this equation here. It's del PL equal to 2 times the shear stress over R. So let me write it down here. So if we have del P over L equal to 2 times shear stress over R, right? So this is what we have from here, right? And then also what we have from the other chapter, we know that 2 is equal to minus viscosity times du by dr, right? And if I just cross multiplication that one, so 2 is going to be del p r, right, over 2l. So now this is 2 and this is 2. So we can say that these two are equal, right? So then it means that 2 is equal to del PR over 2L, which is equal to minus mu du dr, right? And then if we integrate that, great. So if we integrate that, and also if we use the and the boundary conditions and initial conditions that we have, we can say that I think I also, and this is the velocity profile that we have, right? So if we just integrate that one, and this is after the integration. So now we need to find C1, right? So let's use the boundary conditions and the initial conditions that we have. So at R0, right, at the middle of the pipe, the velocity of that one, because if we put R here 0, we get U is equal to C1, right? And we know that in the center line, we have the maximum of the velocity, or we can call it the V of the center line. So let's call it V of the center line. And also at R equal to D over 2, which is at the wall. So if we put in this equation D over 2, so we know that here, because of the no slip boundary condition, the velocity is 0, right, at the wall. So then it means that it should be 0 because of the no slip boundary condition. And if we put that one here, and we also have this one for C1, then what we get from here is, let me see if I have that. So we get the C1 out of here, right? So, and then if we put C1 into the this equation right here, this is what we get, right? So let me also write down C1. So C1 is equal to Vc, which is also equal to del P 16 mu L times D2, right? So this is how we get this formula right here. Okay, now also this is the volume flow rate that we have. And then let me see what else we have here. So okay, for now we all what we did is for the horizontal pipes, right? We did everything for horizontal pipe, but what if we have the non-horizontal pipe? It has um, a little tilted right from here. So if we want to generalize it, this is how we have it. We have a sine theta right here, right? So this is, and also this is the flow rate when we have non-horizontal pipe. Oops. So these are the important of this formula here. And then also if we use the dimensional analysis, so we have these variables here, right? And then if we look at their dimension, we know that we have the R gonna be, for example, MLT, right? It should be 3 then, because this one has the L in it, this one has time in it, and we know that this one has mass in it. So we have all of them. So it's MLT, so R is 3, and then the number of the variables that we have, it's 1, 2, 3, 4, 5. So then K is 5. Then the number of pi that we can find is K minus R, which is 2 right here. And then so this is the number of pi times. So we have the first one here, and this is the first one here, and then the second one here. And now if we use I mean, if it seems kind of reasonable to impose a further assumption to this dimensionless product that we find, in a way that then we can say that the pressure drop is directly proportional to the pipe length, right? We just see it in the figures as well. So it means that then we can kind of say that by using that one and the definition of that, if we say that the pressure drop is directly proportional to the pipe. So let me just write down the assumption here. So the assumption is, we can say that the other assumption that we made, it is laminar flow, it is horizontal flow, we have a smooth surface in the pipe, so we have a smooth surface in the pipe, and now we are saying that the pressure drop is directly proportional proportional to the pipe. So then it means that d times del P over mu V is equal to C. This is how we can make it proportional. C times L over D. And this C, it depends on the shape. We can see it in the, I think in section 8.4, but for the round pipe, C is equal to 32. So we are going to talk about it in the next video. So for round pipe. And then we also have we call it fraction factor. We're also going to talk about it in section 8.4, but this is the formula for it. If we have the laminar fully developed pipe. And what else we have here? So now let's consider the energy equation. So if we consider energy equation, you can see that there is alpha 1 here and alpha 2 here. You've never seen it in the energy equation that we used before, but it was actually should be there. But we just kind of negligible it and say that these are equal to 1 because we use the implicit flow. So right now, if we say that it's a steady state, the flow, and then it's incompressible and there is no shaft work between the two locations, so we can say that it's so here we can say that there is no, okay, so it was HS here, it getting to be 0 because there is no work there, right? And then also we can say that the kinematic energy are the same, so which is this and this here, right? And so this is how we can say that these are going to be 0, because then we're going to say that the kinematic energy is the same. And also because we say that it's in visit cases, so also the alpha is the same, so then these two cancel out, right? And now what else we have? So then if we just simplify this equation, we get the head of loss here, right? And then this is the definition for del P that we already know that. And then also if we look at the shape, we know how to get the Z2 minus Z1. And then if we put all of them in this equation, the head loss equation, we get this formula right here. Or we can use the relationship between tau and pressure drop at the in here, right? We just get it from here, right? We already calculate that. Then this is another way we can express that. Let's see what we have. What else we have? So also we can just let me just simplify this part a little bit for you. So let's say I'm going to cross multiplication there, so we're going to have del P minus gamma times L times sine of theta equal to 2 to L. Okay, this is not a good L. So L and over R, right? And let's say from here, I'm going to this L is not good. Okay, so from here I'm going to factorize gamma. So it means that I have a okay, I'm going to write it down. So I have a gamma here. Then if I factorize it, this one need to have a gamma right there, right? And then it's going to be minus L sine theta, and which is equal to 2 times shear stress L and R. And if we just bring it this one right here, we're gonna get del P over gamma minus L sine theta is equal to 2, 2 times tau L over R, right? So this is also how we can, oh, and there is a gamma, I forgot that, because we just bring it here, right? So this is also how we can write down, and this is, we know that this is equal to HL, right? So HL, oh, sorry, a problem with L apparently. So HL, right? So it means that uh, the head loss is a resultant of the viscous effect, right? We can just see here. So this is how we can also show the head loss. So see you on the next video.